Here I want to identify the inflection points for this polynomial function here. So 12x to the fifth, 15x to the fourth minus 240x cubed plus 6. So to do that, inflection points or changes in concavity, I have to find the second derivative, which tells me about concavity. So first derivative, 5 times 12 is 60, x to the fourth. 4 times 15 is 60, x cubed. 3 times 240 is negative 720, x squared, and then derivative of 6 is 0. And then second derivative of that, 4 times 60 is 240, x cubed is the power now. 3 times 60 is 180, now an x squared, and then 2 times 720 is 1440 x. To find the inflection points or potential inflection points, we got to set the second derivative equal to 0, or look for any places it's undefined. Now, polynomials are defined anywhere, so all I have to do is consider when is it 0. And since there's an x in each term, and let's see, 10 goes into each of these, and I can see like 24 and 186 goes into those. So I was guessing 60 went into everything, and it did. So 60 goes into 244 times, 60 goes into 183 times, and it turns out 60 goes into 1440 24 times. Positive, negative, or positive, positive, negative there. This doesn't factor. You could try to, but I know it doesn't because when I applied the quadratic formula here, I got decimal answers that weren't fractions, whole numbers. So since we factored out the 60x, that means x equals 0 is one of my zeros for this second derivative. And then otherwise, this quadratic, we have to use the quadratic formula. I get about 2.1 for one of the x values and negative 2.9-ish for the other one. And I don't know if these x values are inflection points until I do my test for concavity. So that's what this number line here is for. So on my number line, I plotted my two numbers from the quadratic formula, my negative 2.85, my 0, and then my 2.1-ish here. And then we want to test a number in each of these intervals. So 1, 2, 3 numbers, split the number line into 1, 2, 3, 4 different intervals. And I need to pick a number in each interval to test the sign of the second derivative. So I chose -3, and I found when I plugged in -3 into the second derivative up here, I got a negative answer, so it should be concave down there. When I plugged in -1, because it's between -2.8 and 0, I got a positive answer from the second derivative, so the graph of the original function must be concave up there. Now, you're not guaranteed a change in sign of the second derivative. You got to test every interval to be sure. I plugged in 1 to the second derivative. I got a negative result, which means the original function should be concave down. And then finally, I plugged in 3 into the second derivative, and that gave me positive answer, so it's concave up. So it does change concavity after each of these important numbers here. So that means they are inflection points. Inflection points where we change from concave down to concave up. So what I know about this function is it's concave down to begin with. So if I were to kind of make a rough sketch of this, it's concave down to begin with, and then it becomes concave up, and then it becomes concave down again, and then it becomes concave up again. So this function wiggles, and I don't know how high that relative max is or how high that relative max is. One of these is probably higher than the other. Same thing here. I don't know exactly where that is for the min. I don't know where that is for the min. And these are all local or relative mins and maxes because I know the end behavior of a fifth power is down on one side, up on the other because it's an odd polynomial. So if I have a change in concavity, that means there's a special point in between concave down and concave up, right around here-ish, another point between concave up and concave down, and another point here. Now this point in the middle I can identify easy because that goes with x equals 0. And if I look at my original function and I plug in 0 here, I'm going to get the point 0.6 for sure. To get the other inflection points here and here, I would have to plug in like the negative 2.85-ish into my function to get to the point. Right now, I only have x values of inflection points. I don't actually have the whole point yet. Let's double check a couple of these things on a calculator. So here I've already got some things in Desmos. I typed my second derivative. Notice I'm calling it S for second derivative. And I also typed in the quadratic formula. And I'm usually extra cautious with the quadratic formula with numbers like this. So if I go back to my notes here, I did a bunch of work to get from the 240, 180, negative 440, 1440 to get to the coefficients 4, 3, and negative 24. So I was wondering if I made any kind of error, calculating this right here. So when I use the quadratic formula, I use the original numbers, the 240, the 180, and the negative 1440, and I used my new ones, the 4, the 3, and the negative 24, just to make sure I was getting things right. Always find a way to double check yourself. So you can see my quadratic formula with the big numbers matches my quadratic formula result for the little numbers. I get the same each time. So there's my 2.1-ish number. And then if I change that positive to a negative, I get my negative 2.85. And 0 is also another value that made the second derivative equal to 0 here. And then here's my 4 numbers. I'm testing the concavity, and you can see I get a negative result for the second derivative. So that's a concave down region, positive, which is a concave up region, negative, concave down, positive, concave up. So the next thing I want to do, and I highly recommend you try this too, when you're given a problem like this to look at, do the math, see what your conclusions are, and then look at the graph second to see if your conclusions are right. So now I'm going to go check the graph to see if that's actually true. So here I have the function f of x typed in, and I'm going to turn it on. Let's move it up to the top here of my list. And I don't need to see the second derivative. So I want to see if I can get a scale that shows me those turning points. So let's play with the scale here. We're going to have to go down lower and up higher. So I'm just going to guess at first. Let's go down to negative 100 and maybe up to positive 100. See if we can get any of those turning points. All right, so let's see, I know it's down on one side, right? Then I get some wiggliness in here in the middle at 0. I can see the change in concavity. So this must just go up a lot higher. To try and see how far higher, rather than guess, I can just go in here and say, like maybe f of negative 3 might be where it peaks up there. We could use the first derivative to figure that out. I'm just going to guess here, f of 3. Oh, look at, let's see. Oh, 3 is over here. Yeah, so the min. So I have to go down to like negative 2,000 if I want to see the minimum on the right here. And for negative 3, I'm going to have to go up to like 5,000-ish. So I was way off guessing at 100. You never know. So let's try negative 5,000. Still not far. Oh, that's 500. 5,000. Oh, there we go. That works. Positive 5,000. All right. So I can see some of what's going on in here. All right. So I was, my graph. I'm a little bit off on my graph. So here's my concave up region. And it should be concave up according to my notes. Or let's see, concave down, excuse me, from negative infinity all the way up to negative 2.85-ish. So let's draw a line at 2.85. So I'm just going to sneak in here and say x equals negative 2.85-ish. All right, so here's my concave down region, and then it's concave up over to 0. Oh, interesting. Okay, so it's not a full hump like I was thinking. I only get like half a hump here. Notice it's concave up right to 0 there, but then it switches to concave down again. So my sketch was a little off. I didn't have enough information there because I skipped over looking for mins and maxes probably. And then we have our concave down section, and then at about 2.1 it switches to concave up again. So let's graph that. 2.1 for x. And so right up to about that point right there, it's concave down, and then it switches, or concave, down, and then it switches to concave up again. So, and then again, the other place it switches is at 0 from concave up to concave down. So the graph confirms the analysis. But back to my picture here that I sketched, I totally messed up this section right here because I skipped looking at the first derivative. I didn't check for maxes and mins. So this function, looking at the graph, is probably only going to have two critical values, three critical values, only two of which lead to a max and min, right? Because my function peaked and then it did a little wiggle, kind of went sideways and then dropped down again, minned out, and then came up again. So that's roughly what this looked like. Not bad, complicated, a lot to think about. Keep practicing.